Now we will discuss Wheatstone bridge. A Wheatstone bridge is actually a network of resistances. Say for example, the network is something like this. There is a loop A, B, C, D across which four resistances are connected: R1, R2, R3 and R4. The terminals A and C are connected to a battery, ideal battery of EMF epsilon, and the terminals B and D are connected by a galvanometer G. So this is a simple circuit which comprises of four resistances and a battery. Now the circuit is interchangeable in terms of the battery and the galvanometer. You can always have the battery between the points B and D and the galvanometer between the points A and C, which means that the location of the galvanometer and the location of the battery is interchangeable. For the time being, I am assuming that the galvanometer is connected between the points A and D and the battery is connected between the points A and C. Suppose the battery is capable of delivering a current I, and so the current I, when it reaches the point A, will definitely branch into two different values because the resistances R1 and R3 are different. So suppose a current I1 flows through resistance R1 along AB and a current I2 flows along AD through the resistance R3, which means that I is equal to I1 plus I2. At the point B, the current that enters or flows through the galvanometer is suppose Ig. Now obviously, by Kirchhoff's current law, the current entering a junction must be equal to the currents leaving the junction. So if I1 enters the junction and Ig leaves the junction, it means that a current I1 minus Ig should flow through R2 along BC. If you observe it minutely, Ig and I1 minus Ig are leaving the junction B, which means their sum, that is Ig plus I1 minus Ig, which is obviously I1, is definitely reaching this junction B. So in accordance with Kirchhoff's current law or KCL, the current entering B must be equal to the current leaving B. Similar is the situation of the current which flows through DC. If you note that current entering the point D is Ig and I2, so the sum of Ig plus I2 must leave the junction D. That means the current I2 plus Ig is flowing through R4, and finally at C, current entering is I1 minus Ig plus I2 minus Ig. So minus Ig and plus Ig will cancel, that means I1 and I2 will reach here. The sum of I1 and I2, that is I, will flow back to the battery. Now let us apply Kirchhoff's voltage law in this loop ABDA in this sense, in the clockwise sense, in this clockwise sense, ABDA. So we are moving in the loop along the direction of current I1. So I1 R1 is to be negative, is to be taken as negative because we are moving in this direction, which is the direction of the current. So by KVL, this I1 R1 should be negative. So I have written minus I1 R1. I am moving in this direction, in the direction of Ig. So Ig into G must be negative. Here we have assumed that the galvanometer resistance is G itself. The name of the galvanometer is G and the resistance of the galvanometer is G itself. So minus Ig into G. In this manner, if I follow back to A, I am moving opposite to the direction of I2. So I2 R3 must be taken as positive, I2 R3 must be taken as positive, and the sum of the potential difference is obviously 0 by KVL. So this is our equation 1. Let us now apply KVL in this loop BCDV in this manner. BCDV in clockwise manner. So because we are moving in the direction of current, R2 into I1 minus Ig must be negative. So this becomes minus of I1 minus Ig into R2. I am moving in this direction, which means that I am moving opposite to the direction of current. So I2 plus Ig into R4 is again positive. If I go back to B, I am again moving opposite to Ig. So Ig into G is again positive. Ig into G is positive, and the sum of the potentials is equal to 0. Now, we are actually trying to analyze the Wheatstone bridge from a viewpoint which is called as the balanced Wheatstone bridge. Now, this Wheatstone bridge or this network of resistances is said to be balanced if no current flows through the galvanometer. The bridge is balanced if no current flows through the galvanometer, which means that Ig must be equal to 0, and this is only possible if B and D are at the same potentials. So alternatively, you can say that for the bridge to be a balanced one, the potential at B is equal to the potential at D, so that no current flows through the galvanometer. The galvanometer shows a null deflection. It does not show any deflection. And when the bridge is balanced, we can substitute Ig equal to 0 in both equation 1 and equation 2. So therefore, putting Ig equal to 0 in 1, we get minus I1 R1 plus I2 R3 equal to 0, which means that I1 R1 is equal to I2 R3. This is our equation 1a. Similarly, if we put Ig equal to 0 in the equation 2, what we get is minus I1 R2 plus I2 R4 is equal to 0 because Ig is 0. Now this means I1 R2 is equal to I2 R4. This is our equation 2a. Now if we divide equation 1a by 2a, if we divide equation 1a by 2a, you will observe that I1 R1 by I1 R2, which means that I1 will cancel. You will get R1 by R2 in the left hand side, and in the right hand side I2 R3 divided by I2 R4. I2 will cancel out, you will get R3 by R4. So this is called as the condition of balanced Wheatstone bridge. R1 by R2 is equal to R3 by R4. Alternatively, you can say R1 by R3 is R2 by R4. R1 by R3 is R2 by R4. So when we are applying the condition of a balanced Wheatstone bridge in order to simplify or find the equivalent resistance for a set of resistances, if R1 by R3 is equal to R2 by R4, or if R1 by R2 is equal to R3 by R4, the bridge is said to be balanced, and any resistance along the path BD can be totally neglected because no current will flow through this resistance. So this is a technique of simplifying or finding the equivalent resistance of a network of resistances which are arranged in this manner, and obviously in that case R1 by R2 should be equal to R3 by R4, or R1 by R3 must be equal to R2 by R4. Say for example, here we have a resistance of 5 ohm, 10 ohm, 5 by 10 is half. Here we have a resistance 4 ohm and 8 ohm, 4 by 8 is half. So in that case, any resistance connected across BD can be simply neglected. You can just delete this terminal and analyze the simplification of resistances on the basis of a balanced Wheatstone bridge. Let us solve two problems related to Wheatstone bridge. The first problem is there is a connection of 4 resistances 10, 5, 10, 5, and there is a resistance capital R to which a 6 volt battery is connected via an ammeter. The question is that what should be the value of capital R for which the current in it is 0. Now, if you look at the problem and if you remember the condition of a balanced Wheatstone bridge, then it is quite clear that this is a balanced Wheatstone bridge, because you see 10 by 5 is to 10 by 5 is 2. So the ratio R1 by R2 is R3 by R4 that I have did previously is applicable here. 10 by 5 and 10 by 5. The ratio is same. Or you can say 10 upon 10, 5 upon 5, both are same. This means that there is no current which will pass through the resistance R. So the question that what should be the value of R, it means that any value of R is possible. Whatever be the value of R, no current will ever pass through it, because the resistance network is nothing but a balanced Wheatstone bridge. And so the answer will be any value of R is possible. Any value of capital R is possible. Any finite value, to be precise, any finite value of capital R is possible, because this is a balanced Wheatstone bridge and whatever be the value of R, no current will pass through it. This is a very simple question. It has been taken from H.C. Verma textbook. And this is another problem from H.C. Verma textbook. This is also a network of resistances. 3 resistance 10 ohm and 3 resistance 10 ohm, to which 50 and 50 ohm are connected. The network is connected to a 6 volt battery and there is an ammeter. The question is, you have to find the current measured by the ammeter. Again, if you look at this problem, you see that this segment is again a balanced Wheatstone bridge, because 10 upon 10 is 10 upon 10, which means that no current is flowing through 50 ohm. So if you simplify this will give you the network like 10 ohm and 10 ohm will be in series. Remember that 10 upon 10 is 10 upon 10, so no current is flowing through 50 ohm. So this will reduce to 10 plus 10, 20, and 10 plus 10, 20. And then again this 50 ohm, and then again we have 10 ohm and 10 ohm each. This is 10 ohm, this is 10 ohm. In between now you have 50 ohm and this is 20 ohm. 10 plus 10 is 20 and 10 plus 10 is 20. And to this network you have that 6 volt battery and the ammeter. Now you again see that this is again a balanced Wheatstone bridge, because 20 by 10 is 20 by 10, or you can say 20 upon 20 is 10 upon 10. So again this is a balanced Wheatstone bridge, so no current is passing through 50 ohm, so its presence is meaningless. So this circuit will now simplify to 20 and 10, 30, 20 and 10, 30, and both these 30 ohm resistance are in parallel, so the equivalent resistance will be 30 into 30 by 30 plus 30, or you can say 1 by 30 plus 1 by 30, that is 2 by 30 or 1 by 15, and if you find the reciprocal you will get the answer. So 20 plus 10, 30, 20 plus 10, 30, they are in parallel, so this is obviously 900 by 60, which is equal to 90 by 6, which is obviously 15 ohm. So the equivalent resistance is 50 ohm, so the current will be equal to the potential difference 6 upon the resistance, that is 15, and which will give you 0.4 ampere. So the ammeter reading will be 0.4 ampere. Let us now look at another problem, which is unbalanced Wheatstone bridge. Now it is required to find the equivalent resistance between the points A and B, and if you observe the diagram, it is an unbalanced Wheatstone bridge, because 5 by 10 is half and 10 by 5 is 2. So the ratio R1 by R2 is R3 by R4 does not match here, or you can say 5 by 10 is never 10 by 5. So this is an unbalanced Wheatstone bridge. Now, whenever this type of problem is given, we use Kirchhoff's law, but we use Kirchhoff's law in a modified form to tackle such problems. What we do is, we assume that there is a battery connected between the points across which the equivalent resistance is to be found. So in this question, the equivalent resistance has to be determined between the points A and B. So we assume that an ideal battery is connected between A and B. This ideal battery is, say, of EMF epsilon, which means that the potential at the point A, is plus epsilon, and the potential at the point B is, say, 0 volts, and this is epsilon volts. We can also assume any value for epsilon. Epsilon can be 1 volt, 10 volt, 5 volt, whatever it is. But from a general viewpoint, I am using epsilon volt battery, and which means that this is epsilon, this is 0 volt. So that the potential difference between these 2 points is epsilon. Now, the current that flows from the battery in this direction will branch along AC and AB. Because current which flows along AC means that C cannot be at this potential, D also cannot be at this potential, because the current is flowing. And when current flows, we know that current flows from higher to lower potential. That means there must be a potential difference between A and C or A and D for current to flow through those arms of the bridge. Instead of enumerating currents, we apply the concept of potential difference in order to tackle this problem. So this is epsilon. Suppose this is at another potential difference. Let us call that potential difference as x volt. Suppose the point C is at the potential x volt. And similarly, the potential at the point D is suppose y volt. In Kirchhoff's law, we used the concept of current flow, and then we calculated the potential differences across various resistances, the battery EMF, and we applied KVL and KCL to solve such problems. But it is a slight modified version of Kirchhoff's law, and it becomes easier to negotiate such problems. That's why we are using the concept of potential differences. If you remember Kirchhoff's current law, then it says that the current entering a junction is equal to the current leaving the junction, whereby current entering is taken as positive and current leaving is taken as negative. The same concept will be applied at the point C and at the point D. So, with respect to point C, we can say that the sum of the currents either entering or leaving should be 0. Summation of I is 0. Now, x minus epsilon is the potential difference. We do not know whether x is greater than epsilon or less than epsilon. If we try to solve, we will automatically get x and y in terms of the proper sign. If x is negative, then means it is at low potential. If it is positive, it is at high potential, and so on. So, just ignoring the greater or less value of x and y with respect to epsilon or 0, we just use the concept of currents entering or leaving a junction is 0. So now the potential difference is suppose x minus epsilon. Potential difference divided by the resistance is the current either entering or leaving this point C. So you can say that x minus epsilon by 5 is the current entering or leaving the point C. Similarly, the current entering or leaving the point C along this direction is obviously x minus y by 10. And that flowing along CB will be x minus 0, that is x upon 10. And the sum of the currents is equal to 0 by Kirchhoff's current law. Now, if we simplify it, we will get the LCM as 10, and 10 multiplied with 0 will give you 0, which means this is 2x minus 2 epsilon plus x minus y plus x, which means that 2x plus x plus x, 4x minus y equal to 2 epsilon. This is our first equation. Applying the same concept at the point D, the sum of currents entering or leaving is 0. With respect to point D, we are ignoring whether y is greater than or less than epsilon. As I said earlier, we will get proper sign with respect to which we can realize whether y is greater than or less than epsilon. In a similar manner, we can say that y minus epsilon divided by 10 is the current entering the point D along AD. So y minus epsilon by 10 plus along DC, that will be y minus x by 10, and along DB it will be y minus 0, that is y divided by 5, and this sum of currents entering or leaving is 0. Now again, if you take the LCM 10, it will cross multiply with 0, that will become 0, and what we get is y minus epsilon plus y minus x plus 2y equal to 0, which gives you 2y plus y, 4y minus x is equal to epsilon. This is your second equation. So we have two equations. One is 4y minus x is epsilon, and 4x minus 2y is 2 epsilon. So let us solve these two equations. So 4x minus y is 2 epsilon. This can be written as minus x plus 4y equal to epsilon. Now we can multiply this equation, the second equation, by 4. Let us multiply this equation by 4. So what we get is now minus 4x plus 16y is equal to 4 epsilon. When we add it to the first equation, that means we are adding these two equations, this equation and this equation we are adding. On addition, we get 4x minus 4 is obviously 0, 16y minus y is 15y, and this is 4 epsilon plus 6 epsilon, which means y is equal to 6 upon 15, that is 2 by 5 epsilon. 2 epsilon by 5. So y is 2 epsilon by 5. You can note it down. And now if I substitute the value of y is 2 epsilon by 5 into the first equation, what I get is 4x minus y, that is 2 epsilon by 5, is equal to 2 epsilon, which means 4x equal to 2 epsilon plus 2 epsilon by 5, that is so 12 epsilon by 5, which means that x equal to 4 and 12 divided by 4 is 3, so this is 3 epsilon by 5. So we have found x and y. Now after we have determined x and y, we use the concept of Ohm's law in order to find the equivalent resistance. Let capital R be the equivalent resistance between A and B. So the battery, suppose it delivers a current I. Suppose the battery is capable of delivering current I. And so by Ohm's law, you can write epsilon is equal to I into R. Which means that epsilon is equal to I. Now, I is the current entering the junction A. A part will enter along AC, a part will enter along AB. Some part will flow through this, they will add up, and again you will get the same current I. So you can also say that the current that flows through this junction, this arm and this arm togetherly add up to produce I. Or current leaving this junction and this junction togetherly add up to produce I. So you can use x minus epsilon by 5 plus y minus epsilon by 10 is equal to the current, or you can say x minus 0 by 10 and y minus 0 by 5 is also the current, because the current branches into two parts. A part goes through this, adds up, again a part enters this junction, again a part enters this junction, so they togetherly add up to produce I again. So either you can consider the current as x minus epsilon by 5 or y minus 10 by, x minus epsilon by 5 plus y minus 10 by, y minus epsilon by 10, or x minus 0 by 10 plus y minus 0 by 5. So instead of I, let me use x minus 0 by 10, that is x by 10, plus y minus 0 by 5, that is y by 5 into R. So this epsilon is equal to x. X is 3 epsilon by 5. When we divide it by 10, this becomes 3 epsilon by 50 plus y by 5. Y is 2 epsilon by 5. Y by 5 means it will be 2 epsilon by 25. Obviously, LCM is 50. So this is 3 epsilon plus 2 into 4 epsilon times of R. If you take epsilon common from both sides, it will cancel. 4 plus 3 will get 7. So R becomes 50 by 7 ohm. So the equivalent resistance is 50 by 7 ohm. So this is a technique, you can say it is just a modified version of Kirchhoff's voltage law and Kirchhoff's current law that we have utilized. Instead of enumerating different currents, we use the concept of potential difference. So this is the way of tackling different types of unbalanced Wheatstone bridges. The next problem is a problem from H.C. Verma textbook. Now in this problem, it is required to find the current through all the resistors. We have 3 resistors, 1 ohm, 1 ohm and 1 ohm, and there are 6 battery or cells connected, each of 2 volt. Obviously in this problem we can use Kirchhoff's law to calculate the current in the 3 resistors. But if we use Kirchhoff's law, it will become very complex because there are 6 battery. You have to use the loop rule or KVL and KCL many times, and you will come up with many equations, and then it will be very difficult. So in such problems, we can apply a trick. The trick is that where you will find maximum interconnection, that junction or node can be called as the zero potential or the zero voltage junction. For example, if we try to identify all the junctions in this particular problem, or nodes you can say. So this is one junction, suppose this is junction A, this is another junction, junction B, junction C, junction D, E, F, G and H suppose. So there are so many junctions in this problem. Now, where there are maximum interconnections, if you observe, here there are two connecting wires proceeding along this direction and this direction. In this case also there are two connections proceeding along this and this direction. But at H, G, C and D, there are three connections or three connecting wires which are meeting along this direction, along this direction, along this direction. So at any point or any junction where there are maximum interconnections, that point can be chosen as the zero voltage or zero potential junction. And then we will apply the concept of potential distribution to analyze the current. So suppose out of H, G, C and D, at any point we can choose as the zero voltage point. Say for example, let me choose G as the zero voltage junction. So suppose this is zero voltage junction. This is suppose zero voltage junction. It is at 0 volt. So if this is at 0 volt, then you see that along GF there is only one battery connected. So if this is 0 volt, this point should be at minus 2 volt because the potential difference is 2 volt. 2 volt battery, positive terminal, negative terminal. So this point is at a greater potential, this point is at a lower potential. So that 0 minus of minus 2 is 2 volt. With respect to G and H, a single battery is connected of 2 volt. So this is plus terminal, that is, it is at higher potential and this is at lower potential. So this must be at 2 volt. The junction H should be at 2 volt. So that 2 volt minus 0 volt is 2 volt. Similar is with respect to AH. This is 2 volt potential difference. A is at higher potential, H is at lower potential. So this must be at 4 volt. Because 4 volt minus 2 volt is 2 volt. Now from A to B there is no resistance, there is no electrical component. So the potential will remain same up to this point. So this point B is also at 4 volt. Now with respect to B and C, B is at higher potential, C is at lower potential. Because this is the positive terminal of the battery, this is the negative terminal. As there are no resistances connected, the effective potential difference between B and C should be 2 volt. So this point must be at 2 volt. So that 4 minus 2 is 2. Now with respect to C and D, this is 2 volt, D must be at a lower potential, 0 volt. So that 2 minus 0 is 2 volt battery. With respect to E, D is at higher potential, E is at lower potential. The effective potential difference must be 2 volt, so this is minus 2 volt. 0 minus or minus 2 is 2. Now, we have to find the current in the resistance. If you observe, the current that will flow through 1, 1 and 1. Current flows from one point to another point provided there is a potential difference. But you see that at H and at C, the potential is 2 volt. So they are at same potential, so no current will flow through 1 ohm. Similarly, with respect to points G and D, they are at the same potential, 0 voltage. So no current will flow through this 1 ohm also. Similarly, with respect to F and E, both are at minus 2 volt potential. So no current flows through this 1 ohm either. So we can say that hence we can say that current flowing through all these 1 ohm resistances is 0. Hence current through each of the 1 ohm resistance is